Oops, that's not what I want. There we go. So today is section 5.2, where we're doing the integral of 1 over x. So remember yesterday we said that the derivative of natural log is 1 over x. So if you go backwards, right, then today what we're saying is if you integrate 1 over x, it should take you back to natural log of x. Okay, so our rule is going to be, here we go, the integral of 1 over x takes you back to natural log of x, but we need to put absolute value on that x, because remember, like we said the other day, you can't take the log of a negative, so to make up for that, we just always put the absolute value on inside that natural log. And so the generic form, right, if I integrate u prime over u, that should take me back to just natural log of u. So what I mean by that is, as far as the u prime over u, maybe I'm trying to integrate 2x over x squared plus 5, right? Well, do you see that if the denominator is u, then isn't the top u prime, right? So isn't this in the exact form u prime over u? And if it is, if I recognize that, I can go straight to the answer as the natural log of u. Well, remember, u is the denominator. So this would be the natural log of x squared plus 5. Okay? So that's if you recognize the pattern. Now, what's kind of handy about this is some of them you can manipulate your way in. So let's say, for example, I want to integrate, how about x squared over x cubed plus 2. Okay, so I see the fraction. My first thought is it a u prime over u? Well, not really, because if u is x cubed plus 2, then wouldn't u prime be 3x squared? So if there were a 3 there, yeah, it's u prime over u, and I'm done, right? Well, is it okay if I just put the 3 in there? Well, you can't just change the problem. But what you can do is you can manipulate it so it looks different even though it's equivalent. So if I want to put a 3 up there, what if on the outside I put a 1/3? So technically I'm multiplying by 3 over 3. That doesn't change the value of it. If I do that though, now it's a y prime over y, right? Or I'm sorry, a u prime over u. So I can say, okay, I leave the 1/3 that's out in front. All of this on the inside is u prime over u, right? So when I integrate, it's just going to be the natural log of u, which was x cubed plus 2. So that's kind of handy if you can manipulate your way into it. The only thing is you can only manipulate if it's a constant that you need in there, right? So if there's a constant that you need, fine, you can do it. If there's not, you're going to have to just kind of go through the steps. So what are the steps? Well, remember our list of u substitutions? We're going to add one. You might want to let u equal the denominator. Right? You might let u equal the denominator of a fraction. So look at the example I have here. Here's a fraction. I don't see that it's a u prime over u. I can't separate it, right? There's nothing I can do to this. So I'm going to try my u substitution. I'm going to try and let u equal the denominator. So that means I'm going to be letting u equal x cubed plus 3x squared minus 4. So then du would be 3x squared plus 6x, right? dx. And remember, we do the u du dx. So if I do, let me get this out of the way. So if I do my dx, it's going to be du over 3x squared plus 6x, right? So when I go to rewrite this, I've got the integral. I don't know what to do with that x squared plus 2x on top, so I leave it alone. In the denominator, I just have u. And then in place of dx, I'm going to put du over 3x squared plus 6x. And at first you might say, well, there's a problem. I need the x's to cancel out, right? And I can't cancel those x squareds separately, or those x's separately. But what I could do is, do you recognize that this denominator is like a 3 times x squared plus 2x? Do you see that? And if that's the case, then don't the x squared plus 2x's cancel? Right? Basically, this cancels this. So what I have left is this 3 is going to go to the outside. And then all I have left is 1 over u du. Right? 1 over u du. And what's the integral of 1 over u? Isn't it just natural log of u? So natural log, absolute value of u. And then, of course, final step that I don't want to have spaces, right? We plug our u back in, right? So plug our x business back in right there. Okay, so you might let u equal the denominator. Now, something that comes up in this section is, do we know how to integrate all of the individual trig functions? Well, I know that if I have a trig derivative, I can integrate it, right? Like I know if I'm trying to integrate, let's say, secant squared, right? That's the derivative of tangent, so that just equals tangent, right? But there have to be specific trig derivatives in order for me to integrate them. Well, which of these would that work on? Let's see. I'm gonna see if I can't make this other stuff smaller, so I've got some space here. Can we do it? Ah, look at that. That's handy, right? Okay, so like we know the integral of sine is cosine, right? In fact, negative cosine. And I know the integral of cosine is sine because those are actually trig derivatives, right? But tangent is not a trig derivative. Like I said, I can integrate secant squared and have it equal tangent, right? But I can't integrate tangent. Well, think about it this way. Isn't tangent sine over cosine? So really I'm integrating sine over cosine. And if you look at it that way, isn't it kind of a u prime over u? Right? If u is cosine, then wouldn't u prime be, well, it would be negative sine, right? But that's no problem. How about if I put a negative there and at the same time put a negative out here? So I really haven't changed anything. And so now that it's a u prime over u, I'll bring that negative on the outside. The answer would be natural log of u, but remember u is the denominator, so u would be cosine. Okay, so I've integrated tangent. And just a little side note, if this were a multiple choice, I don't think they would leave the answer like that. I think what they would do is they'd say, well, this negative can go up as an exponent, right, on the cosine. So really I have natural log of, well, what is cosine to the negative 1? Isn't that 1 over cosine, which would be secant? So I think they would write the answer to that as natural log of secant. And I'm not going to do it for you. I think it's in the exercises, but you could do the same thing for cosine. You could just think of it as cosine over sine and then take that through. Okay, the last one you're going to be very excited about, the natural log of secant. There's a way to figure out the natural log of secant. It's several steps, but here's the thing. The textbooks basically say you should memorize it. I don't, because I think there is next to no chance that it's going to show up on the AP exam, so we're not going to worry about it. I mean, technically, College Board says, hey, it's in the list of things you should know, but I've never in, I don't know, 26 years of teaching AP Calculus seen it come up, so we're going to play the odds on that one. Okay, so what have we done today? Well, we've added in two kind of formulas, really only one. We talked about another possible u substitution, right, that might come up, might equal the denominator. There's another u substitution that's going to pop in. We will never be able to integrate natural log of x. We won't. We're not going to be able to integrate natural log of x. So with that in mind, if a natural log of x shows up in an integral, you have to let that be the u substitution. And here's the thing, this one trumps all else, right? If there's a log in there, let it be your u substitution. So on this one, I've got an example here. Notice that it's the natural log of x squared. What I would do is, again, I would do a log property, and I would think about moving that 2 out in front, right, as a log property. Because if it's out in front, then really I can put it out in front of the entire integral. So what I have here is natural log of x over x. Okay, so like we said, let's let u equal natural log of x. That means du is 1 over x dx, right? So dx is x times du. And do you see what's going to happen? Isn't this x going to cancel this x? So when I rewrite it, there's my 2 out in front, and then natural log of x, remember that was our u substitution. So basically, and then in place of dx, I have my du. So all I have to integrate is u, right? So if I integrate that, there's the 2 that was out in front. Integrating u, I'm going to get u squared over 2, and I know those are going to cancel out. So if all I have is u squared, remember, plug back in, u was natural log of x, so I have natural log of x, and the whole thing is being squared. Okay, so I really think it would be helpful if we kind of make this overall summary page, right? When you evaluate an integral, I mean any integral out there, first thing you're going to check, the very first thing we learned in chapter 4 is try to turn any products or quotients into the sum of individual terms. Individual terms. Because if they're individual terms, I can integrate separately. Like, for example, if I have the integral of, say, x times 3x plus 2, right? I can't integrate the x and the 3x plus 2 separately, but what I could do is I could multiply it out and say 3x squared plus 2x, right? Now that it's individual terms, I can integrate each of those separately, okay? Or remember, the first thing we learned about integrating trig functions was we said check to see if they are exact trig derivatives, right? Are they exact trig derivatives? You know, the 6 trig derivatives, like if it's integral of secant squared, right? I know that's tangent. Or if it's the integral of secant tangent, I know that's secant, okay? So is it an exact trig derivative? If it's not, we're going to have to maybe use identities to turn them into trig derivatives, right? So if you can't turn them into trig derivatives. Okay, we said if that stuff doesn't work, then you got some possible u substitutions. The first u substitution we learned was you might let u equal a parenthesis, right? If there's a parenthesis that has an exponent, that's what you're going to let u equal, right? Just the stuff inside the parenthesis. That's the first one we learned. And then the next day we said, okay, well, what if you have trig functions, right? If you can't do the whole trig derivative thing, you might let u equal an ugly angle, right? Or you might let u equal one trig function. Okay, so those are the ones we had learned in chapter 4. And today we just brought in, well, you might let u equal the denominator. And a little hint, if that's what you're thinking, before you go through all the work, look and see if you might have a u prime over u. Because when you let u equal the denominator, frequently they turn into u prime over u problems. Okay? The next one we brought in was we said, hey, if there's a log, it trumps all else. Let u equal the natural log. And then the last one we're going to bring in tomorrow. Okay? So the last thing that I want to mention